Electricity lights our cities at night, runs many appliances in the home, and provides power for electric trains. Where does this power come from? How is it made? To understand this, we must follow these wires back to their source, where we'd find the huge electric generators which provide the power. Like so many other machines which look complicated, the electric generator works by a very simple principle, one which has something to do with magnets. So let's begin by reviewing some of the things we know about magnets. A magnet, you remember, can attract nails and tacks and other objects made of iron and steel. A magnet can also make a compass needle move about. The magnet's force of attraction acts all about it. If we sprinkle iron filings over the magnet, we can see how this magnetic force surrounds the magnet. We call this space in which the force acts the magnetic field. We know that a wire which carries an electric current also has the power to make a compass needle move about, just like the magnet. But the wire can act like the magnet only when electric current is passing through it. Like the magnet, the wire has a magnetic field, but only when there is an electric current in the wire. These iron filings will show the magnetic field produced around the wire when the current is on. Here in this diagram, you see a cross-section of the wire, surrounded by its magnetic field. When a wire is wound closely into a coil and a current is passed through it, all of the wire's magnetic force is concentrated into a small space. Now it can lift these objects with no trouble. But when the current is switched off, the coil loses its magnetic force. It is the electric current flowing through the wire which gives the coil this force. Just as a magnet has a magnetic field about it, the coil of wire has a magnetic field, but only when the current is flowing through the wire. It seems then that electric currents and magnetic fields may have something in common. By producing an electric current in the wire, we get a magnetic field. Let's see if the reverse is true. Let's see if we can get an electric current by producing a magnetic field around the wire. We'll use a magnet to provide the magnetic field. This coil of wire to carry the current, if any, and a very sensitive galvanometer which will act as a detector and tell us whether we've succeeded in producing an electric current, even though it may be a very small one. We'll connect the coil to the galvanometer. And now we'll push the magnet into the coil. Watch the galvanometer needle as we move the magnet back and forth. Moving the magnet into the coil produces an electric current. There is no current when the magnet is held stationary in the coil. Pulling the magnet out produces a current in the other direction. Only while the magnetic field is moving across the coil do we get a current. In this diagram, we can see the magnetic field about the magnet. As the magnetic field moves across the wire, a current is produced, as indicated here by the brightening of the wire. There is no current when the magnetic field is held near the wire. And there is no current when the field is held stationary in the coil. We get a current only when the magnetic field is moving across the wire in one direction or the other. Here you see the same effect, but this time we move the wire instead of the magnet. And to make the magnetic field stronger, we use electromagnets instead of simple bar magnets. Watch the galvanometer needle register the flow of current as we move the wire through the magnetic field. Here is a drawing which shows the same effect. The single wire moving through the magnetic field and the flow of current registering on the galvanometer. We get the same result, again, by twirling a coil of wire through the magnetic field. As long as the wire moves in the magnetic field, we get an electric current. Using the coil of wire, rather than a single wire, concentrates the effect. This very simple method of producing an electric current is called electromagnetic induction. And all generators, however small or large, use this same basic principle. It involves only two strong magnetic poles to provide the magnetic field and a coil which can be turned on an axle. In the actual generators, the coil is made to spin by the power of steam engines or steam turbines, by waterfalls, or by oil engines. As the great coils of wire spin about in the magnetic fields within each of these generators, electricity is produced by the same basic principle we've just seen. From this simple method is produced and sent out over the countryside through wires to farms and factories and homes, to wherever electricity is needed.